Hey guys, this is your fellow maker Jugnu. You can also call me Jay if you like. So this is the second part in the series of videos where I share my experiences and learnings from upgrading my stock Ender 3's mainboard to the MKS Gen L version 1.0 board together with the TMC2208 stepper driver modules. This video will cover the hardware configuration portion of things. A previous video dealt with the firmware or software configuration side. Have a watch if you have not. It is linked down below in the description for your convenience. We are going to start by first removing the stock mainboard, which is located in the casing right in front of the printer. Before we can do just that, we'll need to access the stock mainboard, which is located inside the board casing. We'll have to take off the lid, which is secured by 3 screws. 2 of these screws are located in the front of the casing, while the other one is at the very back, hidden somewhat from view under the printer bed. Loosen all 3 screws in order to take off the casing's lid. You'll notice all the connectors on the stock board are secured down using hot glue. Hence, we'll need to remove these blobs of glue from each and every connector. Using a long nose plier, carefully peel off these blobs from the connectors like so. I have already done this prior, so now I'm just demonstrating. Once we have done that, gently disconnect all the connectors from the board. With that completed, we now need to undo all the cables from the screw terminals. Grab a small flathead screwdriver and loosen all the screws on each and every terminal block. Disconnect all the wires. Using one of the Allen keys provided in the toolset, go ahead and also remove the 4 screws which are holding down the board to the housing. Remove the board and store it in a safe place, preferably in an anti-static bag if one is available. After disconnecting the stock mainboard, we'll now prepare to attach the MKS Gen L version 1.0 board to our Ender 3. Before doing just that, we'll need to plug in our stepper drivers. This is the MKS Gen L version 1.0 board, and these are the 4 TMC2208 stepper driver modules we'll be using in our upgrade. Before plugging in the TMC2208 stepper drivers, let's quickly discuss about step size configuration. The step size on the stock board was set to 1/16 for all the A4988 drivers. We will be retaining the same step size for our use. On the MKS Gen L board, step size selection is set through these jumper blocks found in between the sockets. This is the pin out for each of the jumper blocks. The jumper block pins are divided into 3 pairs, each corresponding to step size selection pins on the A4988 stepper devices. This is an application circuit diagram for the A4988 device from its datasheet. Observe the step selection pins named MS1, MS2, and MS3. Following is the truth table, which shows the selection combination for each of the available step size for this device. In other words, if we were to use the A4988 stepper driver on the MKS Gen L board, then we would need to populate jumpers on pins labeled MS1, MS2, and MS3 for a step size selection of 1/16. However, from the device datasheet of the TMC2208 driver, Observe that there are only two pins which select step size, namely MS1 and MS2. The step size selection combination is given along with the pin description. These combinations, when tabulated into a truth table, look like so. Meaning, to select a step size of 116, we would only need to populate pins MS1 and MS2 on our board as shown. For compatibility with the A4988 stepper drivers, my TMC2208 modules have an unconnected pin next to the MS1 and MS2 pins labeled NC for no connect. This simply means the pin is completely disconnected and isolated for the very purpose of maintaining compatibility with other driver modules. This redundancy in my case allowed me to leave jumpers on the MS3 pins populated without affecting any configuration whatsoever. With that out of the way, let's get going with the stepper module installation. The MKS Gen L board supports 3 axes and up to 2 extruders. This means it is capable of accommodating a total of 5 stepper drivers. These 5 sockets which are laid out here do just that. The leftmost socket is for the x-axis, the one next to it is for the y-axis, this one right in the middle is for the z-axis. The last two house the drivers for the E0 and E1 extruders respectively. Now this is a zoom-in view of the TMC2208 stepper driver module. Note the pins on the far right. The pins GND for ground and DIR for direction. We will be inserting the module such that the GND pin on it mates with the GND pin on the x-axis socket. Similarly, the DIR pin on the x-axis socket mates with the DIR pin on the stepper module. So the orientation will be like so. Carefully push in the stepper module into the socket. Now, insert the remaining 3 modules. With the stepper modules installed, let's discuss about the settings for the reference voltage on the drivers. This voltage is set by turning this potentiometer located on the top side of the stepper driver module. The reference voltage is basically a limit on how much current is allowed to flow through the stepper motor. On the stock board, the installed drivers are the A4988 devices from Allegro. From this device's datasheet, the motor limit current is modeled by this simple relationship. Specifically, the limit current, which is an instantaneous peak value, is a function of the reference voltage and also the sense resistor. The sense resistor for the stock mainboard is of value 0.1 ohms as shown. The individual reference voltage setting of the drivers on my board, together with the calculated limit current corresponding to each, using the previously shown equation, is tabulated here. For verification, I have compared my obtained values to those available on this GitHub Gist site. The link to the site is provided in the description below. This table contains the summary of the stock factory values from that page, in comparison to the values from my machine. I'll be using these values as reference instead for the sake of simplicity. Let's now have a look at the equation for the TMC2208 device. This relationship for the motor current limit during standalone operation is provided in the device's datasheet. Observe that the current limit here is provided as an RMS value instead of an instantaneous peak value. This can be seen from the inclusion of the RMS conversion constant, specifically the 1/√2 in the equation. So in order to calculate the equivalent reference voltage for our TMC2208 drivers as per our stock factory voltage reference for the A4988s, we would need to convert these calculated current limits in the table to RMS values. All we need to do to achieve this is to multiply the individual current limit values with the RMS conversion constant. With this, we have now successfully converted our instantaneous peak current limit values to their equivalent RMS ones. We can now update our TMC2208 voltage reference table with the new values. The remaining unknown is the sense resistor value on the TMC2208 stepper driver module. On my TMC2208 drivers, the sense resistor is of value 0.11 ohms or 110 milliohms as shown. With this information, the updated table now looks like so. We are almost there. Now, we have to rearrange the TMC2208 equation in order to solve for the reference voltage labeled V subscript VREF. This would change the equation as shown after performing some algebra magic. And after plugging in the values for the current limits and also the sense resistor, we now have the completed table with the reference voltage for each of the drivers. Note, we will be using these reference voltage values later on after attaching and connecting the MKS Gen L version 1.0 board to our Ender 3. Next, we will proceed by connecting the MKS Gen L version 1.0 board. Loosen all the screws on the terminal blocks except for the one labeled HE1. Firstly, attach the wires for the power supply and also the hot end fan. For simplicity, I'm connecting my fan directly to the supply input block as it was on the stock setup. Screw down the wires and check that they are securely clamped in place. Observe the polarity as indicated on the board right by the connector. You can damage your hardware if the connection is made against the polarity indicated, so do take note. Proceed next to the bed heater cables. This is the black and red colored wire pair from the bed assembly cable sheath. Once again, pay attention to the polarity. Then, from the other cable sheath, locate and attach the hot end heating element cables. Here the polarity doesn't matter. Observe that I have crimped wire and copper ferrules on the bare ends of my cables. These are linked in the description. With that fastened down securely, connect the parts cooling fan connector to the receptacle labeled fan. Moving on, identify the cable bundle from the hot end section and locate a white colored 2-wire connector. This is the thermistor attached to the hot end. Insert this connector into this black socket labeled TH for thermistor hot end. Similarly, from the other cable bundle, also locate a white colored 2-pin connector. This is the bed heater thermistor. Attach it to this white colored receptacle which is labeled TB for thermistor bed. Following that, let's connect the stock LCD to the board. This is the stock LCD's connector, and this would be attached to this socket over here labeled EXP1. The socket pinout is unfortunately reversed, therefore we would need to connect the LCD in reverse. This is however not possible as the positioning key on the connector interferes with the insertion. What I did was to somewhat remove the positioning key by sanding it down using a nail file. Sand the key such that it is rounded over on all the sides like so. Now we would be able to insert the connector into the receptacle. We are almost done. Let's first connect all the stepper motors. Locate the 4-wire connector labeled X. This goes into the red color receptacle marked X. Next, the connector labeled Y and insert that into this blue socket marked Y. Repeat the same for the Z labeled 4-wire connector. This goes into this green color receptacle named Z. Lastly, plug in the remaining connector which is labeled E into the black socket marked as E0. Finally, we are going to attach all the end-stop limit switches. Observe that the default connectors on the wire end are the 2-pin type, but the MKS Gen L version 1.0 board is populated with 3-pin type sockets instead. In my case, I had access to 3-pin connectors which I used to swap out the original 2-pin connectors with. All I did was to depress the little tab on each connector prong down with a small flathead screwdriver. This then allowed me to pull out the connector prong from its housing like so. After that, I simply push the 3-pin connector housing over the 2-wire prongs as shown. Don't worry about the polarity as it doesn't matter. All that matters is the 2 wires from each limit switch must connect to the pins labeled G and S on their respective sockets as indicated. Don't worry if you don't have 3-pin connectors as you can reuse the 2-pin connectors with a bit of modification. This would require us to cut away one of the locking keys on the connector. This of course makes the connector less reliable in terms of locking down the connection securely. In order to cut off the locking key, clamp the connector in between the jaws of a vise or even a plier. Then carefully slice off the key, which is indicated with a sharp knife. I have not tried this fix myself, and it is merely demonstrated as a suggestion. With that, attach the X-axis limit switch to the red colored socket marked X-, the Y-axis switch to the blue receptacle marked Y-, and finally, the Z-axis switch connector into the green socket named Z-. Okay, that's it. Let's go grab a drink and relax. When we come back, we'll triple check all the connections before applying power. The last remaining step is to tune the pots on the TMC2208 drivers in order to set up the motor limit current. I'm using a multimeter, a length of wire with alligator clips on both ends, and a small flathead screwdriver. A Phillips screwdriver would do equally well, and you would need a multimeter with at least 3.5 digits display capability. Attach one of the alligator clips to the metal base of the flathead screwdriver. Connect the other end to the positive lead of your multimeter. Let's power up our 3D printer. Before going any further, exercise extreme caution when doing this, as the board is powered up and is now at risk from short circuit damage. As such, do not touch the screwdriver on anything except for the pots of the stepper driver modules. We'll first adjust the pot on the X-axis stepper module. Put the negative lead of the multimeter on the USB connector housing. From the table of voltage reference we calculated earlier, set this as close to 0.725 volts as you can. Repeat the same for the pots on the drivers for the Y-axis and then also the Z-axis. The E0 driver would be set to 0.9 volts as indicated in the table. With that, we are now ready to run a test print.